Welcome back to the Deep Dive, where we sift through the noise to bring you the most critical insights. Today, we're plunging into a world that's really changing how we interact with technology. The fascinating, rapidly evolving realm of agentic AI applications. Imagine intelligent systems that can reason, plan, remember, and crucially, act on their own in the real world. The promise is immense, but, well, so are the security implications. Our mission today is to give you a clear, actionable path to understanding how to secure these powerful digital collaborators. And to guide us through this pretty intricate landscape, we're diving deep into an indispensable resource, the OSP Gen AI Security Project's Securing Agentic Applications Guide. This isn't just academic theory, folks. It's a practical blueprint for anyone building, deploying, or defending these systems. It's like getting a peek into the future of AI security right now.
It truly is.
Yeah.
And what's really crucial to understand, I think, is that securing agentic AI isn't simply an extension of traditional application security. It's fundamentally a new challenge. Unlike static software, these agents operate with significant autonomy. They remember past interactions, they engage in multi-step planning, and critically, they leverage external tools to interact with the world. All of this creates entirely new attack surfaces and risks that demand a specific, tailored security approach.
That makes perfect sense. So for you, our listener, our goal is clear. By the end of this deep dive, you'll not only grasp the core components that make up an agentic AI system, but also the unique threats they face, and most importantly, the robust strategies for designing, building, and operating them securely. Okay, let's unpack this and start with the architecture itself. To truly secure any system, you first have to understand what it's made of, right? So let's start by breaking down the key components that come together to form an agentic AI application as meticulously defined in the OWASP guide. Think of these as the fundamental building blocks of a thinking, acting digital entity.
Absolutely. At the very heart of any agentic system is its brain, the generative language models. These are your sophisticated LLMs like, say, GPT-4 or Claude, responsible for understanding, reasoning, planning, and generating responses. We also see multimodal LLMs, which can interpret images or audio, and even smaller language models, SLMs, specialized for particular tasks. And many agents also utilize fine-tuned models, which, undergo additional training to hone their capabilities, sometimes even using techniques like supervised fine-tuning, SFT, to reduce those frustrating, out-of-scope or irrelevant answers.
Okay, so we've got this incredibly powerful AI brain, but how does that brain decide what to do and then, execute those decisions in a structured way? How does it orchestrate its actions and plan its steps?
Right, that brings us to orchestration and the reasoning planning paradigm. Orchestration basically dictates the agent's overall behavior. This could be a pretty straightforward workflow where tasks follow a predefined sequence, or could be more complex hierarchical planning, where a central orchestrator breaks down a big task and delegates parts to specialized subagents.
Like a manager.
Exactly like a manager. And for reasoning and planning, this is how agents tackle complex tasks step by step. The guide highlights some fascinating paradigms like React. That's where the agent dynamically interleaves reasoning steps with actions. Very clever. There's also chain of thought, CoT, which is that step-by-step thinking process, much like a human might use. And even tree of thoughts, TOT, which explores multiple reasoning paths in parallel, complete with look ahead and self-evaluation. Pretty sophisticated stuff.
Okay, reasoning, planning. But what about remembering? Agents need context, right?
Absolutely essential. For an agent to be truly effective and consistent over time, it needs a way to retain information that's its memory. You've got short-term memory, handling the immediate context of a conversation, and then long-term memory, which stores past interactions or external knowledge. What's particularly interesting and a significant security consideration are the different types of memory sharing. This ranges from simple in-agent session memory, which is quite contained, all the way up to cross-agent, cross-user memory.
That sounds risky.
It carries the highest risk, if compromised, because it's shared across multiple agents and potentially multiple users. Many systems also use retrieval-augmented generation, RG, often with vector databases, to give agents access to vast external knowledge bases. Helps keep them grounded in facts.
Got it. But agents aren't just thinking and remembering in a vacuum. They interact with the actual world. How does that happen?
That's where tool integration frameworks come in. These frameworks allow agents to extend their capabilities by using external APIs, calling functions, accessing data stores, basically interacting with other systems. We see this with flexible libraries like LangChain or CrewAI, which provide building blocks for developers, or even managed platforms like Amazon Bedrock Agents or the Microsoft Copilot platform, which offer more abstraction and maybe easier integration within their ecosystems.
So they have tools.
Exactly. And these tools, in turn, operate within a specific operational environment, which defines the scope of their capabilities. This could be anything from basic API access, executing code on a server, interacting with databases, or browsing the web, all the way to, controlling PC operations like file systems and OS commands, or even in highly specialized scenarios, operating critical systems or accessing IoT devices. Each of these capabilities offers immense power, but simultaneously introduces specific, significant risks.
Okay, here's where it gets really interesting for me. For each of these powerful components, there are specific, unique threats outlined in the guide. Understanding these connections is absolutely vital for defense, isn't it?
Indeed. It's crucial. When we look at the generative language models themselves, KC1, two key threats are T5, cascading hallucination, where, one wrong bit of info snowballs, and T6, intent breaking. This one's particularly fascinating and, frankly, dangerous. Instead of just protecting against an attack or forcing our system to do something bad. With intent breaking, the threat is about manipulating the agent's own reasoning, making it choose to do something harmful while believing it's fulfilling its original purpose.
Wow, so it's tricked into wanting to do the wrong thing.
Precisely. It's a paradigm shift from forced error to manipulated intent. For memory modules, KC4 T1 memory poisoning is a direct attack where malicious data is injected, leading the agent to make bad decisions based on corrupted memory. And when it comes to tool integration frameworks, KC5 T2 tool misuse is a core vulnerability. This often leads to serious issues like T3 privilege compromise or even T11 unexpected remote code execution if an agent is tricked into using a tool in an unintended or harmful way.
So understanding these core components, the LLM, orchestration, memory tools, environment, and their associated threats, is truly your first step. You can't protect what you don't understand, and these elements are like the fundamental DNA of Agentic AI. Now that we've broken down the building blocks of Agentic AI and pinpointed their inherent weaknesses, the next logical question is, how do we assemble them securely? The guide really emphasizes a holistic approach where security isn't an afterthought, but rather it's baked into the very architecture itself.
Precisely. You can't just bolt security on later with these systems. Let's look at some fundamental secure architecture patterns that are common across various agentic frameworks. The tool use pattern is central, obviously agents using external APIs or functions. Then there's the reflection pattern, which allows agents to introspect, evaluate their past actions, and self-correct. It's a crucial self-defense mechanism, really.
Like learning from mistakes.
Kind of, yeah. Or at least recognizing something went wrong and trying a different approach. Then the retrieval augmented generation, or ARAG, pattern enhances agents by pulling in relevant info from external knowledge bases for more informed responses, significantly reducing the chances of hallucinating or making stuff up. And a really critical one is the user privilege authentication assumption pattern. This means agents assume the permissions of the invoking user. This is absolutely vital for maintaining granular security and preventing, an agent from doing something the user themselves couldn't do.
That's a good overview of the core patterns. How do these patterns then manifest in different agent architectures? Do they give them distinct characteristics and, different security profiles?
Absolutely. The guide highlights a few key types. The sequential agent architecture is the simplest. A linear workflow, maybe a single language model, probably just in-agent session memory, limited API access. Think of it as a single-minded assistant following a script. Pretty basic. Then you have the hierarchical agent architecture, or role-based multi-agent systems. This is more complex. You've got a central orchestrator breaking down tasks and delegating them to specialized sub-agents.
Back to the manager analogy.
Exactly. Here you'll likely see multiple language models, definitely hierarchical planning, and probably memory shared across those agents like that project manager delegating to a team of specialists. And finally, there's the collaborative agent swarm, or distributed agent mesh. This is where multiple peer agents work together without a strict hierarchy. They engage in multi-agent collaboration, often using things like tree of thoughts for exploring solutions, and typically involve memory shared across agents and sessions with very flexible tools. Imagine a team of equals collaborating dynamically on a really complex problem. More autonomy, but also potentially more complex security challenges.
It's clear how the choice of architecture profoundly impacts security. To make this tangible, the guide walks us through a multi-agent Copilot application case study. Could you maybe walk us through that?
Sure. Picture this. You have an orchestrator agent. It uses hierarchical planning, language models, flexible libraries like LangChain maybe, and cross-agent session memory. This orchestrator delegates tasks to specialized agents. One for your calendar, one for email, one for Slack, one for Google Drive, let's say.
Okay, specialized roles.
Right. And these specialized agents operate with limited API access to their respective services. This is key. They use predefined API calls where the language model might generate some parameters, like the date for a calendar event, but not the entire API call structure itself. But even with this constraint, there are significant threats. For instance, T2 tool misuse can still occur. A malicious prompt could trick the language model into generating harmful parameters within those allowed API calls, potentially leading to API vulnerabilities or unauthorized operations, like deleting the wrong calendar event or sending an email to the wrong person with malicious content.
Oof. Even with limited scope.
Exactly. Then there's T6 intent breaking and goal manipulation. An attacker might manipulate the orchestrator's LLM to generate parameters that serve a malicious purpose, even if those parameters technically fit within the allowed API scope. And if language model-generated parameters include user identifiers, maybe an email address, or a user ID T9 identity spoofing and impersonation becomes a very real risk through clever prompt injection.
That's a powerful illustration of the real-world risks. And while many frameworks exist to help build these LangChain, CrewAI, AutoGPT, or even managed services like Amazon Bedrock agents, it's crucial, isn't it, to understand their default security posture and the trade-offs between customization and abstraction. This makes me wonder, how do you ensure security isn't just a feature you add on, but a foundational element woven throughout the entire development process?
That's the critical question, really. Security isn't an afterthought here. It absolutely needs to be embedded from the very beginning. The OWASP guide really emphasizes a life cycle approach, integrating security from initial design all the way through to operations. Let's start with the secure design and development phase. First up, system prompt engineering and hardening is absolutely critical. It's all about clearly and securely defining the agent's core instructions and limitations. You use clear delimiters like XML tags or triple backticks to separate system instructions from unpredictable user input. Explicitly state what the agent should do and, crucially, what it should not do. Consider allow lists for specific topics or functions to prevent it straying off course.
Like guardrails in the prompt itself.
Exactly. Another vital aspect is human-in-the-loop, or HITL, design. For any high-impact actions, think sending emails, modifying databases, executing code, spending funds, updating critical memory, you must identify where human approval is necessary. This means designing clear, user-friendly interfaces for that review step and leveraging any built-in HITL features within your chosen frameworks. Don't just let the agent run wild with critical actions.
Makes sense. What else in design?
Memory security design is essential. You need to plan how to protect that stored information, short-term, long-term, shared from unauthorized access and tampering. This involves robust access control, thinking about IAM roles or API keys, encryption for data both at rest and in transit, and thorough input validation before storing any data in memory. You don't want poisoned memory.
Okay, so that's design. Moving into the secure build and deployment phase. What are the priorities there?
Two big ones jump out: environment hardening and sandboxing. This means executing agent code in isolated environments. Think OS-level containers like Docker, lightweight virtual machines like Firecracker, or even WebAssembly runtimes. The goal is to restrict file system and network access to strictly what's needed, containing any potential breaches should a compromise occur. You limit the blast radius.
Containment is key.
Absolutely.
Yeah.
Coupled with this is just-in-time, or JIT, access, and ephemeral credentials. This is all about drastically reducing the window of opportunity for credential misuse. You grant permissions only when they're truly needed, and for the shortest duration possible, think short-lived API tokens instead of long-lived static keys. Minimize the exposure.
Right, limit the time any credential is valid. And then we get to operations.
And finally, yes, the secure operations and runtime phase. This demands continuous vigilance. Continuous monitoring anomaly detection goes beyond just checking if the agent is up or down. You need to monitor the prompts themselves for telltale jailbreak techniques. Observe the tool calls for unusual frequency or suspicious parameters. Keep an eye on memory updates for any signs of tampering. Integrating these signals with your SIEM system or security monitoring tools is crucial for spotting attacks in progress.
So, active defense during runtime.
Precisely. Then there are runtime guardrails and automated moderation. These enforce policies dynamically while the agent is running. This means implementing input and output guardrails to block or sanitize malicious content, using memory time to live, TTL, to automatically expire old or potentially stale data, and maybe PII redaction to protect sensitive information flowing through the agent. And one more thing becoming critical: AI bot mitigation and controls. As agents become more active online, interacting with websites or other agents, how do we know they're legitimate? This includes establishing a tamper-proof agent identity layer. The guide mentions using cryptographic request signing like RFC 9421 message signatures and potentially an agent name service, an ANS, to ensure agents can be verified as trusted collaborators, not just another potential threat vector.
This holistic, full lifecycle approach is absolutely essential, isn't it? What really stands out to me is that securing agentic AI isn't a one-time fix, not just a checklist item. It's an ongoing commitment across the entire development and operational journey. It's about constant vigilance and adaptation.
You've hit the nail on the head. It's a continuous process.
That's a solid overview of the lifecycle approach. Now let's get even more specific. We mentioned the operational environment earlier, the different ways agents interact with the external world. Each interaction point brings unique risks and therefore requires tailored controls, right?
Precisely. Generic controls aren't enough. Let's zero in on a few impactful examples from the guide's key operational capabilities, KC6. For API access, KC 6.1, the core threats are pretty clear. Unauthorized data access or leakage, API abuse, that's T4 misinformation or T2 tool misuse, and of course compromised API keys leading to T3 privilege compromise or T9 impersonation.
So what are the controls?
Several layers. First, you must enforce least privilege using fine-grained OETH scopes or specific limited API keys or roles like specific AWS IAM roles. Don't give the agent keys to the whole kingdom. Set up allow deny lists for the APIs the agent can actually call. This prevents manipulation where an attacker tricks the agent into calling some unexpected malicious API endpoint, and crucially, prefer API templates over letting the language model generate the entire API call structure from scratch. With templates, the LLM might only populate established parameters, not invent the whole call. This drastically reduces the risk of malicious API construction.
Okay, templates are safer. What about executing code? That sounds inherently risky.
It is. For code execution, KC 6.2, the core threats are T11, unexpected remote code execution, often leading to T3 privilege compromise, and also direct code injection via T2 tool misuse. The controls here have to be strict. Mandatory sandboxing is non-negotiable use containers, VMs, WebAssembly, whatever isolates that code execution effectively. You should also perform static analysis on any agent-generated code before execution, using tools like Bandit for Python or semgrep. Catch obvious vulnerabilities, enforce strict resource limitations, CPU, memory, execution time to prevent denial of service or runaway processes. And of course, for any high-risk code execution, require human-in-the-loop approval, seriously.
Absolutely. And what about controlling the actual computer the agent might run on, like file system access?
Yeah, controlling PC operations, KC 6.5. The threats are unauthorized file access or modification, T3, and arbitrary OS command execution, T11, T3, T2. Big risks. Controls here mirror the code execution ones, but at the OS level. Apply strict isolation using OS-level sandboxing, maybe running the agent process as a highly restricted user with minimal permissions. Implement strict allow deny lists for permitted OS operations and crucial file paths. Don't let it wander the file system. Limit the accumulation of sensitive data within the sandbox itself. Enhance monitoring significantly for any OS-level actions. And again, consider HITL approval for critical operations. You don't want an agent accidentally deleting system files, right?
Definitely not. These granular controls are incredibly important, but thinking back to those multi-agent systems, particularly the swarm architectures where there's no central orchestrator, how do you establish trust and identity in such a decentralized environment? That sounds like a whole new level of complexity.
It is a fascinating challenge, isn't it? How do these agents, operating without a central command, truly know who to trust? Which other agent's information should it accept? This is precisely where decentralized identity and trust comes into play, specifically mentioned under memory sharing patterns like KC 4.3.2. The guide points towards emerging standards like decentralized identifiers or DIDs. These are a W3C standard allowing agents to have a persistent, verifiable identity that they control themselves without relying on a central authority like a corporate directory.
So self-owned identity for agents.
Exactly, self-sovereign identity.
Yeah.
And paired with DIDs are verifiable credentials, or VCs. These are like digital attestations. An agent can use a VC to prove specific attributes, capabilities, or maybe trust levels granted by another entity, again, without needing a central checker. This combination is fundamental for enabling secure inter-agent authentication and tracking the provenance of information or actions. It allows agents to verify each other's claims and capabilities in a secure, decentralized manner. It's still evolving, but it's likely key to the future of complex multi-agent systems.
If we connect this to the bigger picture, It's crystal clear that securing agentic AI isn't just about protecting lines of code or locking down individual components like the LLM. It's about carefully managing every single interaction, every tool call, every piece of memory, and ensuring verifiable trust at every level of autonomy and interaction. It really feels like a paradigm shift in security thinking.
It absolutely is.
Wow, what an insightful journey we've been on. We've really taken a deep dive into the OWASP Securing Agentic Applications Guide, exploring everything from the fundamental components of agentic AI, the LLMs, orchestration, memory, tools, and their inherent risks. Through secure architectural patterns and the entire development lifecycle, right down to specific controls for critical operational capabilities like API access and code execution, and even tackling the complexities of decentralized trust.
The key takeaway, I think, is profound. Agentic AI introduces fundamentally new security surfaces that go way beyond traditional language model concerns, like prompt injection, though that's still relevant. Their persistent memory, their capacity for autonomous planning, and their extensive use of tools demand a proactive, holistic approach to security, one that integrates controls right from the initial design, through development and deployment, all the way to continuous runtime monitoring and response. The OWASP guide provides really practical, actionable steps that are, frankly, indispensable for both builders and defenders navigating this rapidly evolving landscape.
This has been incredibly insightful and truly highlights the unique challenges but also the opportunities in this space. As these AI agents become more autonomous and, deeply integrated into our daily lives and even critical systems,
Well,
how do we developers, security teams, users ensure they remain our trusted collaborators, enriching our capabilities, and not become unintended adversaries in an increasingly complex digital world? Definitely something to mull over until our next deep dive.